What we want to talk today is about not about like discrete distributions that I mean when I have point charges, but what happens when we have continuous charge distributions. The similar way that like we did when we studied like a Coulomb's law here. Remember that we study here and we just generalize the concept of the behind the principle of superposition to a continuous charge distribution using the integration. We are going to do exactly the same here. Right? Just get we are going to generalize the concept of the principle of superposition that we have here. And we are going to apply this for three different kinds of symmetries. So this is for line distribution, surface distribution, and volume distributions, like the same way like we did before. The only thing that we have to find here is actually those uh, line density, line charge density, the surface charge density, volume charge supply. To consolidate, right? This is didn't right. I'm going to find volume and just have to apply that concepts images. And the main trick here, guys, is actually find right this correct the correct. Can you give me a second? 1 second. Sim. Não. Cidade. Então, espera. Sorry. Was guys, okay, the main again the same challenge that we face here in the first lectures and the problems that we face in the first and the problems connected related for our first lectures is actually how to represent right these infinitesimal elements of lines, elements of phase, and then volume. That as long as you do not make any mistake when you are finding when you are trying to find function for those elements, it's going to be some hard work. In this case, guys, let's see if we have time. We have okay, you have 18 minutes. I think this is more than enough. I'm going to make another problem for you. Is I'm going to try to find the electric field to a charged disk. This is a classic problem. And to do that, I'm going to use previous result. Why I'm doing that? I'm doing that just to save some. Of course, I'm trying to save here some work. Otherwise, it's going to be very long. So you can check in your book. But if you don't want to check in your book, you can go back right to lecture one, to the first lecture, and I solved that right. I solved for the ring of charge right here, as you can see right. Solve this problem for you guys. Okay, so for that problem. And what I'm doing, I'm just going to start from this point, and then I'm going to electrical field. I found the for the for the force, right? As you can recall, the force. But you know that actually the force, all we have to do is just multiply the charge by the electrical field. So that means that electrical field just divided by the test charge. And then you can actually easy this expression here. And I'm going to start from here. As you can see, the main point here is actually representing the infinitesimal elements of charge. That means we have to be careful when representing this, guys. The main point here, right? And then we start from the definition, right? So this is going to be surface distribution. First of all, you have to realize that the surface charge distribution density, sorry, surface charge density is the amount of charge divided by the area. But we are interested in infinitesimal element here, so that means that these infinitesimal element of charge sigma infinitesimal element of, okay, and of course we can not one going to be a guy here too. And we have to write this element of area too, but this is a area of particular ring here, right, with this thickness dr. So this is going to be 2 pi r dr. You can subtract that, and we are going to find that equal sigma, that is density multiply to minus this pi r r. If you integrate, okay, now you can substitute both the fraction. So this is going to give us like electric the electric field is going to be integral big R of Q of dr d squared 3 over 2. Okay, this is kind of easy integral, right? You can rewrite this that this is here. Technology helping to accelerate our job here, so I don't have to. I'm going to here on the numerator here, so this minus. Well, now is easy. Have to see. So this is going to give me sigma over 2 epsilon 0 multiplied by 1 minus squared Okay, we're back. Just to finish here. Just to finish this part here, guys. What we're going to have is this electrical field here. So it's going to be the direction. Of course, I did it here, but here that this in the direction. Again, remember, as physicists, we're kind of interested in extreme cases, And in this case here, we can analyze as here. Um, we can analyze here for the case where the big R goes to infinity. If this goes to infinity, that means that this term here, right, term, this term here vanished. This term is going to zero. What does it mean physically? That means that you have very infinite, right? Going to infinity. Oh my God. Try to make that means that all this the is increasing, increasing, and increasing. What you have is actually you have here is infinite plane, right? Or confusing thing factor. It's increasing. So that means that what you have, you can actually approximate that as an one infinite plane, infinite shape. And then in this case, and this is a very important result, I'm going to put this result in red as that from one infinite plane, the electrical fields, of course, is going to be only function here of the surface charge density and the free space permittivity. And when is this important? Guys, this is going to be in the direction that means in this case perpendicular to the plane. Why is this important? We are going to study, and you guys already did in high school, like an electrical component that is called capacitor. And this is the mathematical form of the electrical field generated by a capacitor. So to understand this, so that's the one of the main of is the major significance in this case. First of all, yeah, of course we have like for this kind of case you have the electrical field that is perpendicular to the plane. It dependent only in the electric density and and this is a characteristic the the medium around the plane, right? And this is going to help us to understand the capacitor. I'm not going to use explain, I'm going to use the model. But I'm not sure that you guys learned this in electrical field like a capacitor, but I think you guys did actually. Maybe not using this kind of tools and so on, but probably you were pres- presenting the electrical field, and capacitor. So just that's all I wanna say today. I had one more thing like planned for you guys, was to explain the what happens when you have a dipole in one electrical field, but we don't have time for that today. But it's kind of easy, right? What is going to happen is actually that this dipole is going to rotate. Clearly, you can see that the summations of the dipole and the dipole balanced. But the same is not true for the torques, and that means that the dipole is going to rotate. When you put a dipole inside like electrical field, it's going to rotate, and it's not kind of any kind of arbitrary rotation. It's going to be a very particular rotation that is going to be periodic. But what is going to happen with this dipole is that this dipole is going to what you're going to see, this dipole going to describe like a simple harmonic motion, the same like we saw in chapter 15. That means that this dipole, I'm just going to show you guys. Oh, something like that, and going back. Oh, okay, guys. So I hope you have a fantastic week. I decreased the number of problems you have to do until next week because we have only 1 week. But try your best to solve all the problems, especially the problems that involve concepts that are not familiar, or concepts that we didn't learn in high school, especially those involving like a continuous charge distribution. Okay, my friends, see you around. You have fun. Bye. See you next class.
Thank you.
Thank you,
No
Professor.
problem, guys. No problem at all. If you have anything, please let me know. Send me a message or something. All right. And I'm recording the classes. I still didn't have time to upload, but as soon as I upload, I have to edit the videos and so on. Then I'm going to send to you and revise on your own. Okay, guys. Have fun. Bye.